Okay, so in order to get this, Einstein came up with something called the equivalence principle. So Newton said that all objects fall, no matter regardless of mass, fall at the same rate in a uniform gravitational field. So they all fall at the same rate during the gravitational field regardless of mass. Einstein said that there is, with Einstein's equivalence principle, he said that you cannot tell the difference that an observer in, let's just say, a box, a closed box in an elevator, freely falling observers cannot tell whether they are freely falling in a gravitational field or whether they're out in space. This is the equivalence principle. So, for example, if we have an elevator, so the guy's in an elevator, and this elevator is on the Earth. He's acting out with gravity. If he jumps up, then he'll get pulled back down. However, if he's in an elevator in free space, moving at the acceleration of gravity upwards, like no matter what they'll think, like there is no experiment that could tell the difference between these reference frames, between the two reference frames. So if there's another person up here and they drop a ball, it's going to fall down to the ground, accelerating at g. If this person lets go of a ball, it's going to since they're moving upwards at gravity, at the speed, acceleration of gravity, it's going to fall down. They're going to look the exact same.
I have a question.
Yeah.
Is this restricted to the gravitational force? No.
No.
No, it's just the same amount of acceleration.
Yes. Yes. So they're equivalent. So now let's picture the idea. So let's have a rocket ship. Let's just say this is accelerating at gravity, at the speed of gravity. Now there's a person in here. So if a light beam goes through, what happens is since this is moving up, the light beam will be going straight, but in the rocket's frame, it'll look like it's curving down. So and it leaves the rocket at this place here. So now we could switch our frames and say, rather than, due to the equivalence principle that we just saw here, which you guys all agreed on, there was no disagreements in there. So if we're in a gravitational field, the light would enter and get curved down. And it will leave at the same spot as if this was accelerating. Okay, so this comes back to Newton's equation. G m1 m2 is r squared. So light should not be affected by this. Light should not be, so gravity is just the attraction between massive objects, and light doesn't have any mass. According to Newton, this shouldn't work out. But according to the equivalence principle, there's nothing wrong with this picture. So one of them is right. So there was an experiment done. So here's the sun. Glasses, some shades. Here's the Earth. And during a solar eclipse, so they measured the position of the star. So theoretically, it should have been over here. So this is the actual position of the star. But when we looked out, we saw this star that's supposed to be here, over here. So this is the appeared position.
This is during the solar eclipse, right?
Yeah. So what happens is the light beams emitted from the star actually gets curved by the sun's gravitational field. So now, it appears to look right here. So this light got affected by the gravitational field. It got curved by gravity, which according to Newton, that's not supposed to happen. So this is the experiment that proved Einstein to be correct. What's up?
Who did that?
Arthur Eddington.
There we go.
Who?
Sir Arthur Eddington.
Very proper. But okay. So we saw that light affects time. We saw that changing light affects time. So let's look at clocks.
I have a question.
Go up.
So that's